Welcome back to this series on the stiffness method. In today's lecture, we are going to focus on a very specific but very crucial step, and that is assembling all the local stiffness matrices into the global structural matrix. This is the point where all our local formulations come together to represent the full system. So just starting off from the wider sequence of steps needed to solve structures using the stiffness method, we've already started with bar and beam stiffness and developed them and coded them, and we're working our way through global and local systems, and eventually we'll solve displacements and forces. Today the scope is just one step in the process, adding beam and frame members into the global stiffness matrix. Before we start the assembly, let's quickly remind ourselves what we're assembling. To demonstrate how to add the stiffness matrices for each element to the stiffness matrix for the whole structure, we start by looking at a structure made up of beam elements. As a reminder, this is the stiffness matrix for any beam element, which we developed fully in the previous lecture. In this case, we're also looking at a structure where the local and global coordinate systems coincide. That means the members are not rotated. Rotation will be the next topic we address. The 6x6 matrix represents how forces and moments relate to displacements and rotations at the element's two end nodes. We'll now see how these local matrices are placed into the correct positions in the overall structure. Now that we have the stiffness matrix for an individual beam element, we need to think about what happens when several beam elements are connected to form a structure. Each element has its own stiffness matrix, but when two or more elements meet at a node, their stiffness contributions overlap. This is the central idea behind assembling the global stiffness matrix. We take each element matrix, identify which global degrees of freedom it connects, and then add its contributions into the global system. The process relies on a consistent numbering system for nodes and degrees of freedom. Once this mapping is in place, the assembly becomes systematic. Each element matrix is slotted into the right place in the global matrix. Let's demonstrate how to add element stiffness matrices to form the stiffness matrix for the whole structure. We'll look at this beam with three nodes at the key points of interest. Node 1 is the pin support, node 2 is the roller support, and node 3 is at the end of the overhang, where we have 2 point loads, one in the x direction and one in the y direction. This means that we have 2 elements in total. Both of these will contribute to the global stiffness matrix. Each element could have a different cross-section, material, length, or moment of inertia. And that is why the stiffness matrix for each element is numbered separately to reflect its own properties. Now let's draw on all the degrees of freedom. Since this is a beam element, each node has 3 degrees of freedom: axial, transverse, and rotational. With 3 nodes, each with 3 degrees of freedom, we have a total of 9 degrees of freedom in the structure. And that means that the global stiffness matrix for this structure will be a 9-on-9 matrix. Now that we've set up the problem, let's look at the 2 elements in this structure. Element 1 connects node 1 to node 2, and element 2 connects node 2 to node 3. Each element has its own 6x6 local stiffness matrix based on its properties. These could be different. For example, element 1 might have different cross-section, material, or length compared to element 2. When we assemble the structure's matrix, we place the stiffness contributions of each element into the global matrix according to the global degree of freedom numbering. For element 1, the degrees of freedom are those belonging to nodes 1 and 2. For element 2, the degrees of freedom are those belonging to nodes 2 and 3. So at node 2, both elements meet. This is where the contributions overlap. The overlapping stiffness terms are added together in the global matrix, enforcing both compatibility and equilibrium at the shared node. So through this systematic process, each element matrix is positioned and summed into the overall 9x9 structural matrix. Here we define the stiffness matrix for element 1. Element 1 has a length of L1, a modulus of elasticity E1, and a moment of inertia I1. Using the standard beam element formulation, we can write out its 6x6 local stiffness matrix. This symbolic form makes it clear how the stiffness of the element depends directly on its own material and geometric properties. Now we'll define the stiffness matrix for element 2. Element 2 has a length of L2, modulus of elasticity of E2, and a moment of inertia of I2. Again, using the standard beam element formulation, we can write it 6 by 6 local stiffness matrix. At this stage, both element 1 and element 2 have their own local stiffness matrices, expressed symbolically in terms of their properties. These two matrices are the building blocks that we'll now assemble into the 9 by 9 global stiffness matrix for the structure. We start the assembly by mapping element 1's local stiffness matrix to the global stiffness matrix K. First, we fix a clear global degree of freedom numbering. For each node, we list the degrees of freedom in their order, U, V, theta. With 3 nodes, this gives 9 degrees of freedom and a 9 by 9 matrix. Node 1 has degrees of freedom 1 to 3, U1, V1, theta 1. Node 2 has degrees of freedom 4 to 6, U2, V2, and theta 2. And node 3 has degrees of freedom 7 to 9, U3, V3, and theta 3. Element 1 connects node 1 to node 2, so its local degree of freedom order is U1, V1, theta 1, U2, V2, theta 2. And these map directly to the global degrees of freedom 1, 2, 3, 4, 5, 6. We denote the global stiffness matrix by capital K. Each column of K gathers the force responses associated with a single global degree of freedom. So when we assemble, we add full rows and columns from the element matrix into the corresponding rows and columns of K. Now we match the degrees of freedom on the local matrix to the global matrix and place the terms accordingly. For example, the local K33 rotation at node 1 maps directly onto the global K33. Local K44 maps directly onto global K44. And local K56 maps directly onto global K56. At this stage, only the rows and columns 1 to 6 of K receive contributions because element 1 only touches nodes 1 and 2. Rows and columns 7 to 9 remain 0 for now, but they'll be filled when we assemble element 2. On the stiffness matrix for the second element, we again notate the columns and rows and then place the matrix terms into the full matrix based on the degree of freedom numbering. If there is already a term in the global matrix at that position, the new contribution is simply added to it. And this happens because element 2 shares node 2 with element 1, so their stiffness contributions overlap at those degrees of freedom. When the local term for node 2 axial displacement maps into K44 in the global matrix, it adds on to the existing value from element 1. A coupling term between the transverse displacement and rotation at node 2 appears as K56, again by adding to what is already there. And a new entry for node 3 rotation appears at K99, since this degree of freedom belongs only to element 2. We can now see how the structural matrix takes shape. Element 1 has contributed stiffness terms into the rows and columns associated with nodes 1 and 2. Element 2 has contributed stiffness terms into the rows and columns associated with nodes 2 and 3. At node 2, where the two elements meet, the overlapping degrees of freedom mean that the contributions from both elements have been added together. At nodes 1 and 3, the contributions come from only the single element connected to each node. By systematically mapping each element matrix to its corresponding row and columns in the global system, we can complete the assembly of the full 9 by 9 stiffness matrix. Let's demonstrate this once again, but with some numbers this time. So we're taking a beam with 3 nodes at key positions of interest. Node 1 is the pin support, node 2 is the roller support, and node 3 is at the end of the overhang with 2 point loads. And once again, 2 elements. There are 3 nodes and 3 degrees of freedom, so we have a total of 9 degrees of freedom, which means that the stiffness matrix is a 9 by 9 matrix. In this example, all geometric and material properties are given for each element, and that means that E, the cross-sectional dimensions, and hence A and I, and lengths L1 and L2 are known. So each local 6 by 6 stiffness matrix can be evaluated directly, numerically, once the mapping is clear. Because the local and global axes coincide in this worked example, so there's no rotation of any element, the degree of freedom mapping is direct. With all properties specified, we can now proceed to compute the element matrices and assemble the 9 by 9 global matrix K numerically. First, we'll separate the structure into its elements and write the local stiffness element matrix for each element separately. As we know the material and geometrical properties for each element, we can calculate the numerical values for each member of this matrix. On this slide, we bring both element stiffness matrices together into the full global matrix. Element 1 contributes to the block of global matrix covering node 1 and node 2, so degrees of freedom 1 to 6. Element 2 contributes to the block covering node 2 and 3, so degrees of freedom 4 to 9. At node 2, both elements connect to the same degrees of freedom, axial, transverse, and rotational. And this means their contributions overlap in the global matrix. And when this happens, the values from each element are added together. So, as you can see in this example, the coupling terms from both elements are added together. And you can see this in every other overlapping node. By combining the two element matrices in this way, we can see how the global stiffness matrix is assembled step by step. The overlap at node 2 ensures continuity of displacements and equilibrium of forces, tying the two elements into a single structure. And here we can see the completed global stiffness matrix for our example structure. It's 9 by 9 because we had 3 nodes and 3 degrees of freedom at each node. The contributions from element 1 appear in rows and columns for degrees of freedom 1 to 6, which belong to node 1 and 2. Contributions from element 2 appear in rows and columns for degrees of freedom 4 to 9, which belongs to node 2 and 3. And as we mentioned before, at node 2, the overlapping terms from both elements are added together. The result is a single global stiffness matrix K, which fully represents the behavior of the structure under loading and boundary conditions. And this completes the assembly step for the example. From here, we would normally move on to apply load, solve for displacements, and then recover reactions and internal forces. But we'll do that at the next stage in the stiffness method. This slide shows how the global stiffness matrix is built up step by step. The shaded area highlights where the stiffness terms for each element are placed in the global matrix. For element 1, the shaded block corresponds to degrees of freedom 1 to 6, representing nodes 1 and 2. For element 2, the shaded block corresponds to degrees of freedom 4 to 9, representing node 2 and node 3. As each element is assembled, its terms are mapped directly onto these rows and columns. At node 2, the degrees of freedom are shared, so the overlapping contributions are added together in the global matrix. The red or empty areas represent entries that are currently 0. These positions do not receive any contribution until another element is connected to those degrees of freedom. It is important to stress that this example is for elements arranged sequentially in a straight line, where the local and global coordinate systems coincide. That means the mapping is direct and there is no need for rotation of the element stiffness matrices. Rotation will be introduced later in the next lecture. Now that we've seen schematically how the global stiffness matrix is assembled, let's look at implementing this process in MATLAB or Octave. The logic is straightforward. We'll start with an empty global stiffness matrix filled with zeros. Its size will be determined by the total number of degrees of freedom in the structure. We'll loop through each element in the structure, identify the 2 nodes that define the element, and determine the corresponding global degrees of freedom. We'll add the element stiffness terms into the global matrix at these positions. If the position already contains a value, the new term is simply added on, just as we saw in the shaded example. This coding approach replicates the process we carried out manually. Each element stiffness matrix is mapped into its correct block, zeros remain in all unused locations, and overlapping contributions at shared nodes are summed. In this way, we build up the global stiffness matrix for the full structure automatically. Let's get to it. Here we look at the first steps of the code. We always begin by preparing a clean workspace. We remove all variables from memory, close any open windows, and clear the command window so we start with a blank screen. Any line that begins with a % is a comment, and comments are not executed, they're just there to explain the code. Commands that end with a semicolon will run but suppress output from being printed in the command window. This keeps the script tidy, especially when dealing with large matrices. On this slide, we'll set up the input for the structure before we assemble the stiffness matrix. We begin by telling the program how many elements and nodes are in the structure. In this case, there are 2 elements and 3 nodes. We'll be doing the example that we just solved by hand. We also specify that each node has 3 degrees of freedom: axial, transverse, and rotational. Next, we define the element-to-node connectivity. This tells the program which nodes are connected to which element. For example, element 1 connects node 1 to node 2, and element 2 connects node 2 to node 3. We then set up a table called n, which numbers the degrees of freedom assigned to each node. The code runs through each node in turn and labels its degrees of freedom consecutively. Node 1 is given degrees of freedom 1, 2, and 3, Node 2 degrees of freedom 4, 5, and 6, and Node 3 is given 7, 8, and 9. And you can see this in the output that I've copied from the program. The numbering is crucial because it creates a direct map between each element's local degrees of freedom and their positions in the global stiffness matrix. For example, as you can see here, element 1 connects nodes 1 and 2, and its degrees of freedom will be 1, 2, 3, 4, 5, 6. Element 2 connects nodes 2 and 3, so its degrees of freedom are going to be 4, 5, 6, 7, 8, 9. When we assemble the global stiffness matrix, these degrees of freedom tell the program exactly where to place the terms for each local stiffness matrix. On this slide, we define the geometry and material properties for the structure. These inputs are the values used to calculate the stiffness matrices for each element. We start with the lengths of the element L. Here we have two spans, so element 1 is 2 meters and element 2 is 3 meters. We enter these as a vector, 2, 3. Next, we define the modulus of elasticity E. In this example, I'm assuming that both elements are made from the same material, steel, which has a modulus of 200 gigapascals. We'll write this as a single value and then expand it to a vector of length num-Ls, or the number of elements, so that both elements are assigned the same property. It's important to note that if the elements had different materials, we could just as easily define E as a vector with different values, just as we did for the lengths. We then calculate the cross-sectional area A. As I said, I've given this a cross-section of 20 by 20 millimeters, and this gives an area that we can convert into square meters. Again, assuming both elements have the same section, but we could easily define A as a vector with different values for each element. Finally, we calculate the second moment of area, or the moment of inertia I, using b to the power of 4 divided by 12 for the square cross-section we have. For 20 millimeters converted into SI units, this gives our base value. Once again, we expand it into a vector assigning the same value to both elements. But just like with E and A, we could define this as a vector with different values for each element if required. The key point is, for L, E, and A and I, we can either assign the same property to every element or specify a vector if the values vary across the structure. This makes the code general and flexible. Here we generate the local 6 by 6 stiffness matrix for each element, using the geometry and material properties we defined earlier. We begin by pre-allocating space. K local equals 0's 6, 6 num-L's, number of elements, and this reserves one 6 by 6 matrix for each element in the structure. Inside the loop, the code does the following for each element: extracts its length, LE, calculates the axial rigidity, EA, and calculates the flexural rigidity, EI. It then builds the full 6 by 6 stiffness matrix for a 2B beam element in local coordinates. Finally, this is stored in the variable K local, so that each element has its own stiffness matrix saved in this 3D array. Because in this example the local and global coordinate systems coincide, the members are arranged in a straight line without rotation. No transformation is needed at this stage. And now we assemble the global stiffness matrix K from the element stiffness matrices. First, we calculate the total number of degrees of freedom. So NDOF total is the number of nodes times the number of degrees of freedom. In this case, with 3 nodes and 3 degrees of freedom per node, this gives 9 degrees of freedom. We then initialize the global matrix as a 9 by 9 zero matrix, so K equals zeros. We can also optionally store each element's global degree of freedom indices for bugging or inspection. This can be very useful for checking that the assembly is being done correctly. Then inside the loop over the elements, we identify the 2 nodes of the current element, and for those nodes we collect the corresponding global degrees of freedom indices called the DOFs. So for example, element 1 has degrees of freedom 1, 2, 3, 4, 5, 6. Element 2 has 4, 5, 6, 7, 8, 9, and these are stored in the memlock for reference if needed. And finally, we assemble the stiffness matrix. This means we add the local 6 by 6 stiffness matrix of the element into the correct block of the global 9 by 9 stiffness matrix. Where elements share a node, for example, in our case a node 2, their stiffness contributions are added together in the overlapping rows and columns. This ensures continuity of displacements and equilibrium of forces at the shared node. By the end of the loop, the global stiffness matrix K is fully assembled for the structure. And now that the assembly is complete, once we run the program, we can display the global stiffness matrix. The The program prints a header line to show the size of the matrix. In our example, it tells us that the global matrix is a 9 by 9. And next we can see the output format in engineering notation. This makes the numbers easier to read. They're given in powers of 1,000 with 4 significant figures, which is standard in engineering calculations. And finally, we display the matrix itself. What we see is the fully assembled global stiffness matrix with the contributions from both elements combined. This is the matrix that represents the stiffness of the entire structure. And here we can see the final assembled global stiffness matrix displayed. If we compare these results with the example we solved earlier by hand, the beam with a span of 2 and 3 meters, we can see they match exactly. This is an important step. Whenever we write code, we should always check it against a worked example where we already know the answer. It's the best way to make sure that our program is assembling and calculating correctly before we use it on a larger or more complex structure. At this point, it is pretty easy to go back and adapt this code to any straight beam where the local and global coordinate systems coincide. On this slide, we can see that the exact same script can be run in Octave, which is a free open source alternative to MATLAB. The commands we've used are fully compatible, so you don't need to change anything in the script. The assembly process and results, which are the global stiffness matrix, are identical. This is really useful if you don't have access to a MATLAB license. You can practice, test, and verify your stiffness method code in Octave and be confident that the results are the same. The important point is that the method is general. Whether you use MATLAB or Octave, you're applying the same logic and you'll obtain the same global stiffness matrix for the structure. In this lecture, we saw how to assemble the local stiffness matrices into a global structural one, both by hand and also by coding our own little program. In the next lecture, we'll extend this process to structures where the local and global coordinate systems are not aligned. That means taking local coordinates and rotating them into the same coordinate system as the full structure. This will allow us to analyze structures that are not just on a straight line, but rotated at any angle in the plane. Join me next time for that.